Good morning, everyone. First of all, thank you very much for coming to attend my talk. It's an honor and a pleasure to be here with you today to talk about natural language processing at Airbnb. So just to give you a quick and brief intro to myself, my name is Avneesh, as you've already heard, and I've been at Airbnb for more than 2 years now. Over there, I mainly work on problems in the natural language processing domain across different product areas. And that's actually what I'm going to be talking about today. I'm going to be talking about various NLP problems at Airbnb and how we used deep learning to attempt or to solve some of these problems. So actually, I'm going to be talking about a few different projects today, and they all culminate to the final point over there, which is representation learning for listings. In other words, how do we encode the unstructured information on a listing page at Airbnb into, say, a fixed size vector or embedding on which we can do all sorts of interesting things. But what I wanted to emphasize also is that this is not really, or the selection of topics I'm going to talk about today is not fully representative of the entire range of machine learning or natural language processing projects we do at Airbnb. There's a lot of stuff already in production in terms of, customer service ticket routing and search relevance and the like. This is actually, a lot of these projects are a lot more on the research side of things. So the focus is actually more on some cutting edge stuff we've been doing, and that's actually either currently in the process of getting integrated into the product, or over the next year will be integrated into the product. And in fact, the unifying theme here is that this is all work that the AI lab at Airbnb, of which I'm a founding member, has been doing. So as I mentioned, that the emphasis is a little bit more on research and prototype-driven development. The mandate of the lab is really to kind of connect, the recent advances in artificial intelligence and machine learning with various product areas at Airbnb. And the way we work is we kind of build prototypes, and then we partner with various product teams to then integrate those prototypes into the actual Airbnb product. So as I mentioned, there's an actual theme here, and the theme is actually about how we can impose some kind of structure on the unstructured data on an Airbnb listing page. So I first will talk about listing descriptions and titles and what we do with those. Also what we're doing with reviews at the moment. Also a little bit about multimodal learning and combining images and reviews together to come up with some very interesting projects. And as I mentioned, this all builds up to the final point of how we can kind of combine various task-independent representations of pieces of components of a listing into a unified representation for the listing that we can do all sorts of interesting things with. And so in each section, what I'll do is I'll talk a little bit about the work that we've done here, or the ongoing work that we're doing. We'll talk about, some of these things will be naturally speculative. I'll give some context to the problem at hand. I'll talk about the approaches we used and the implementation, and where available, I'll also provide some results. And as I mentioned, the emphasis, as you can tell from the title, is on natural language processing, but there are obviously lots of other applications of neural networks at Airbnb, most notably in the computer vision domain, and we are actively investigating those. All right, so now to start off, I'm going to talk a little bit about what we did with listing descriptions and titles on an Airbnb listing page. So if we actually look at a wide variety of listing pages, there's a significant problem in some kinds of listings. In particular, listing titles can often be vague and uninformative. So if we look at 2 examples here, the first one I would say is actually a very informative listing title. It tells you that you are well located to public transportation. It tells you about maybe the aesthetics or the decor or the feel of the apartment, whereas the second I would argue is not really informative at all. And so, obviously there are 2 problems, I guess, with vague and uninformative listings. The first is oftentimes these kinds of listings don't get booked. If they don't get booked, neither the host nor Airbnb makes money, so this is bad for us. And it's also, a more subtle problem is that it's a little bit harder for us to kind of index some of the listings with uninformative titles. So if you think about on Google, if you go and type, San Diego beach house, the thing is it's pretty difficult then for you to actually retrieve relevant listings, unless the actual title contains the word San Diego and beach house. There might be some further indexing that's done down in the listing descriptions, but the idea is, can we actually ideally summarize the description and generate better titles that could also optimize SEO? So two of these examples are essentially, the first one, or two of the applications are first, suggesting kind of good titles in the list your space flow. So as users set up their, new listing on Airbnb, we can kind of figure out and tell them, okay, maybe based on the description you wrote, look at these titles because they're likely to kind of generate more revenue or increase bookings for you, and also from an SEO perspective. The third point actually, or the third application is kind of what I mentioned before, is the fact that there are, in the process of actually kind of summarizing what I would say, or mapping from descriptions to titles, we can actually also extract embeddings or vectors that represent the information contained in the listing description. And with these embeddings, we can do all sorts of interesting things downstream, and I'll talk a little bit about that. All right, so first of all, how exactly do we do this mapping from descriptions to titles? The approach we use is essentially inspired from the CMNLP paper from a couple of years ago, a neural attention model for sentence summarization. In fact, that is what we are doing here. We are summarizing, where when mapping from a description to title, one consider almost always, in fact, even as per the rules on the site, the title is pretty much, or not almost always, but the title is pretty much always shorter than the description. And so we can think about the title as being a summary of the description, and then just simply learn a mapping from description to title. In other words, we're doing abstractive summarization here. So this is actually an instance of sequence-to-sequence learning, which many of you may be familiar with. The original sequence-to-sequence learning papers were first proposed in the context of neural machine translation, but nowadays we literally use them everywhere in all sorts of different applications, and this being one of them. So the basic architecture is actually, very similar to an autoencoder, except I would say instead of trying to reconstruct the original input, you're actually trying to construct the title. Or in other words, what you're doing is you're maximizing the likelihood of the title given the description. So if we actually, so if we actually kind of take a look at this example, what we need is we essentially go through our site and extract all description title pairs. This is an example of a description title pair, including, kind of spelling mistakes and the like. And we simply learn this model to maximize the negative log likelihood of the title. So in other words, we maximize the log likelihood of the title given the input, given the description, and this is itself parameterized as a recurrent neural network language model. So this is essentially a recurrent neural network language model, except we condition, in addition to conditioning on the previous word when generating titles, we also condition on the embedding that the encoder provides us. In other words, the embedding of the listing description. So this is the embedding over here, and we can actually do some very interesting things with these embeddings. Another thing to note is actually we can use this technique also to for all sorts of interesting text applications. So one thing we've also used this for is to come up with representations of customer service tickets, because oftentimes customer service tickets that come in via email have a body as well as a title. So we can actually use the same technique to also learn representations of tickets, and then we can then integrate this into our CX product or our customer service product to be able to retrieve similar tickets given an incoming ticket. So for example, agents can figure out if previous tickets were solved in certain ways, maybe I should also be doing the same thing. All right, so here are a couple of examples of this model that we trained, basically, and there's the model out. I provide the input, the model output, and the real title. So you can actually see here that at least in the first instance, I would argue that perhaps they might equally be descriptive. The real title emphasizes the pool aspect, whereas the model output actually emphasizes the location. And you'll see that, it says located a short walk from Orchard Road. That essentially summarizes it as near Orchard Road. The second example is actually something that is a lot better than the real title. So the real title actually, I believe, referred to the actual street name in a particular town in France that the listing was in, which is really not very descriptive in terms of telling me what's unique about that listing. But if you look at the model output, I would argue that, because of the emphasis of nature and so forth, the model really gets it right by saying, a charming house in the countryside. So the actual model is generating very reasonable titles, and so we're currently in the process, as I mentioned, of integrating this into the list your space flow to suggest to potential hosts what good titles they could use, as well as for SEO. I mentioned also, and as you saw in the model architecture, at the end of the encoder, or when we kind of go left to right through the description, at the end we kind of get an embedding that represents the encoder hidden state. And what can we do with this embedding? Well, the nice thing is, if it's a vector, we can do things like clustering and k-nearest neighbors. And actually, that's something that we've done over here as well. So we looked at kind of qualitatively evaluating some of these embeddings. In the instance on the left, it might not be immediately clear, but these two listings, I would argue, and having looked at the actual listing properties themselves, are luxury listings. So they contain, 6, 7 bedrooms, pools, jacuzzis, and the like. And that was kind of captured in the description. Whereas this is something in London. It's more of an urban listing, 3 bedrooms, so relatively large for an urban listing, but doesn't have the luxurious amenities that the others do. And the similarity, roughly speaking, is about this is about 3 times more similar than the non-luxury listing. So this is maybe a few hand-picked examples, but we really did see some of the phenomena here. We also built an embedding evaluation tool, and this one is actually a lot more kind of large scale, and we can kind of take a look at similar listings based on an input listing. And I'd like to emphasize that the similar listings retrieved here are solely based on the listing description text. They're not based on any other modalities on the listing page. So you can see here that, even though the images differ, a lot of because the descriptions are quite similar, it actually retrieves listings that I would argue are somewhat similar across many different geographies, mind you. So this may not we're obviously not going to integrate this in the product at this level, because I don't think if you're looking at Thai listings, you would want something in Herzliya in Israel. But a lot of the commonalities and regularities between the descriptions are picked out, and we managed to see that qualitatively as well. All right, so I talked a little bit about what we did with descriptions and titles. We came up with this cool way to generate titles using just established sequence-to-sequence learning techniques. Of course, with attention, it doesn't really work without attention very well. Now let's see what we can also do with another piece of text on a listing page, and that is the reviews. So with the reviews, what we can actually think about is a review oftentimes does not simply talk about a single topic, or in the literature of kind of reviews, people call them aspects, but aspects can literally be thought of as topics. But basically, reviews never talk about a single topic, or if they do, they're often very short. If they're of any decent length, they often talk about multiple things at the same time. So if we look at this example here, we see a number of different kind of topics or aspects that are revealed in this review. We first look at host responsiveness. We look at cleanliness and size. We look at amenities as well here. And, optionally, I've also marked them with an additional sentiment marker. So some things might be more positive and negative here. So obviously, a review is a mixture of these different aspects, and sentiment can also vary along these aspects, although I would also argue that sentiment can often be tacked on to the model and is not necessarily a core part of revealing the actual aspects. But the basic idea is, how exactly can we take in a review like this and in an unsupervised way figure out what the aspects or what the topics are? And maybe what then we can do is, if we can then represent a single review as a mixture or a distribution over aspects, that could be one way to encode the information in review. So we could talk here and say, maybe this is like 40% about amenities, and maybe this is 30% about cleanliness, and the remaining are kind of split between, say, size and host responsiveness. But this is ideally what we would like to kind of get out of some kind of an aspect extraction here. And now there's several solutions we can explore. The classic kind of literature for topic models will often talk about LDA and latent variable models and the like, and we can definitely do that here. But what we decided to do instead was to adopt a slightly simpler kind of variant from, in terms of not really using latent variable models. Here, this is actually taken from a paper at this year's ACL about, where the authors presented a model that they called attention-based aspect extraction. So I'll spend a couple of minutes just walking you through the model and exactly what it does here. So like I mentioned, the traditional ways to kind of look at this are using LDA, although one would often argue that if you look at kind of like the topic clusters that you often get with LDA, they're not very easy to interpret. There often is very little coherence amongst words and the like. And so the motivation behind this work is, can we build an autoencoder style architecture, so in other words, continue to make this an unsupervised learning problem, but actually try and reveal topics or aspects that have a lot more coherence. And so the basic idea is, the first step what we do is we actually use what is known as like a self-attention mechanism. Basically what it allows us to do is look inwards introspectively into a sentence and figure out what are the words that are really relevant or important in the sentence for downstream applications. So we're going to actually use a self-attention mechanism to construct the input representation of the sentence. And the way we do that first is we first take every word in the sentence, we remove stop words and so forth, but we convert them to their word embedding, and then we take a simple average bag of words representation of that sentence, and we're going to call that Y. This is what they call in the paper the global sentence context. The next thing we do is then we compute attention, and we use a multiplicative form of attention here between the global sentence context and every word as represented by its word vector, and we pass it through a softmax. So basically now we have a distribution over sentences. So we have an attention distribution, which we call A, and then the next step is we essentially just do a weighted sum product, and we use that attention distribution now to come up with a sentence embedding that includes the attention, and that's what we call ZS. So this is the attention-based encoder part, and then what we then do after that is we want to now say, okay, if we have a matrix T, which essentially represents the various aspects that we have, and T is what is essentially a K by D matrix, where K is the number of aspects that we choose, and D is the dimensionality of the word embedding space. So note that the aspects are actually K points within a D-dimensional space, or within the original word embedding space. We can simply just learn an autoencoder now that says, okay, here is my sentence representation that I came out from the attention module, and here's this matrix T that represents aspects. Then there's a vector P, which essentially represents the mixture or the distribution over my aspect embeddings. And so what we can essentially do is we have parameters A, and as you can see, A depends on M as well, and we have the word embeddings, which we can pre-train and fine-tune, and we also have parameters T and P that we then learn. So essentially this is the model. It can be done in a completely unsupervised way, and what we can then do is we can take that matrix T, which represents the aspect embeddings, and we can go row by this matrix. As I mentioned, it's a K by D matrix, so there are K rows where K represents the number of aspects. And so for every aspect, what we can do is we can take the row vector and say, okay, it's in the D-dimensional space, tell me what my nearest neighbors are, and it'll essentially give me the words, because I'm in that D-dimensional space, that are closest to that particular aspect embedding. And here we have some very interesting coherent examples of aspects. So, going through a bunch of review data, we managed to reveal things like, for example, these are all relevant to outdoors. This might be relevant to aesthetics, host friendliness, and the like. It's interesting to note that while this model doesn't explicitly take into account sentiment, you could extend the architecture that I showed previously to probably do that. What it does do, though, is if you actually carefully choose the number of aspects, what you will reveal is often clusterings of words that represent positive and negative clustering. So what I didn't show here is, for example, you might have a positive aesthetics aspect, and I would argue that these are all positive sentiment words, but then you will also reveal a similar negative aesthetics aspect, ugly, crude, things like that, basically. And so if you carefully choose the number of aspects, you could reveal some very interesting characteristics here. And so now there are a couple of representations that we can use downstream. The first representation we can can use is that mixture distribution. So we can use the vector P, for example, for a given review to tell us what the mixture or the distribution over aspects is. We could also use this guy over here, which is the sentence embedding taking into account the attention weights. So there are a couple of different representations of the review text that we can use downstream. All right, so I've spoken actually about a couple of different text modalities. The first text modality I spoke about was listing descriptions. I presented a method to map from descriptions to titles, and I talked about how we can actually extract the embedding from the encoder part of that encoder-decoder framework to then use that embedding downstream to represent information in the listing description. I presented a similar approach to learn embeddings for reviews. Now what we're going to talk about is we're going to move a little bit more towards non-text modalities. So this is kind of a stepping stone towards how we can model, potentially image embeddings and structured attributes and the like. And I'll get to that towards the end of the talk where we talk about listing representations. But this project is kind of a stepping stone in that direction. So let me first motivate this project with an interesting kind of product idea. So the idea I talk about here is what I call visual reviews. And the basic motivation is if you think about when you're on Airbnb and when you're kind of trying to shortlist, you're going to say Berlin and you have 5 listings that you now have shortlisted and you want to decide which amongst those 5 listings. Many times what people do is they first look at the images of a listing, followed by what other guests say about that listing, the reviews. So the idea over here is to fuse those decision-making points together across multiple modalities, across images and text, fuse them together and enhance the decision-making process. And the way we propose to do this is basically when you go onto a listing page, to be able to click on an image and then have on, say on a side-by-side view, relevant snippets from the reviews also from that listing that talk about the content of the image. So to make this concrete, here we have an image of a deck with some deck chairs with a view over the ocean. And people talk about his home has 2 outstanding patios overlooking the ocean with recliner chairs and everything to make it a perfect place to relax. So wouldn't it be cool if we could actually place that side by side? All right, so I'll talk a little bit about how we did this. There are a couple of different ways to do this. And I'll first talk about a discriminative model that we basically used, which is essentially a variant of the multiple image caption generation models that were very popular a couple of years ago. And then I'll talk about a multimodal latent variable model that is actively ongoing research. All right, so the first idea and the first approach is what we can do is we can bootstrap from an image caption model. An image caption model is actually very similar to the description to title model that I spoke about before, except instead of mapping descriptions to titles, so instead of just mapping text sequences to text sequences, I'm going to map images to pieces of text. So multiple modalities. The nice thing about neural networks is we can really they're very modular, so we can take out stuff and add things very easily. So that's essentially the motivation behind a lot of these image caption models. So the basic idea, first of all, is to go through our data firstly and figure out what good image caption pairs are. There are a lot of bad image caption pairs. This is one of them. You can't really read the text here, so I've blown it up. So what it says is, this is actually the caption relevant to this. We appreciate our guests and do our best to provide an authentic local Airbnb experience. Nothing to do with the image. Whereas this is actually what I would argue is a good caption. Lower patio looking up at the tower, and it is exactly what it describes. So we implemented a number of heuristics to then filter through a bunch of our image caption pairs and figure out which ones are good image captions, good image caption pairs, and threw away the bad ones. And then, what we then did is we decided, you can pick your favorite image caption model. So the choice that we used was essentially this paper from PAMI 2016, which is the show and tell model. There have been subsequent improvements to this, for example, the show, attend, and tell model. And in fact, we kind of implemented, because the initial results weren't so good, we actually implemented a variant of this model that actually is pretty much a stepping stone towards that show, attend, and tell improvement. So basically adds some kind of attention to it. So essentially, essentially we have this model that is a sequence-to-sequence model. On the left-hand side, we have some kind of output of, choose your favorite image, image network like a VGG or ResNet or one of those kinds of guys. And then on the right-hand side, we have an LSTM that conditions on the image embedding and generates the caption. And so this is essentially a discriminative model because we're trying to maximize the likelihood of the caption given the image. And so we essentially go through a bunch of image caption pairs and we do that. Now, the problem is, like I mentioned, is that if we actually did, before actually I get to the problems, what we do is we first train this image caption model, and then now that we have this model, we can say, okay, this model actually allows us to compute likelihood of text conditional on an image. So what I'm going to do is I'm going to feed it review sentences. So I'm not going to say, okay, you've trained it on image captions, that's cool, but then I'm going to give you a review sentence, and I'm going to say, conditional on this particular image, how likely is this review sentence? So we can actually compute conditional likelihoods, conditional on a given input image, and we can rank review sentences, therefore, by this conditional likelihood. So this is essentially a way for us to kind of rank reviews or review sentences based on the content of images. And if we just do this naively, essentially if we just take the model that I described before and just apply it to, train it on good image caption pairs and then apply it to review sentences, we don't really exactly get what we want. If we look at the left-hand side, we see essentially some very generic sentences are ranked pretty highly. Quiet, clean, spacious, well located. Only this one is what I would argue is relevant to the image here, which is essentially a balcony with a view over this town. And so what we need to do is we need to mix in what we need to do is we need to mix in the image embedding at multiple stages of this LSTM. As you see here, the LSTM kind of goes through left to right through a sequence of words and scores each one. So, and initially in the model, the image embedding only was used to initialize the LSTM and that's it. But what we did was subsequently we got this arrow and we pushed it into each of these other LSTM steps. Like I said, this is kind of a poor man's version of attention. Ideally, what we'd like to do is in the show attend and tell paper to focus on kind of different parts of the embedding, or sorry, of the image when actually generating the output text. But this was actually a quick and easy thing to do. And so we tried this and we got some slightly better results. So more relevance here, two balconies, still a little bit of irrelevant kind of information or review sentences here, something also over there. The next thing we actually did was, so what we essentially noticed is, okay, we have generic sentences that are getting ranked very high. So let's do the following. We can come up with, because in the LSTM I essentially go left to right and I evaluate individually the log probabilities of every word conditional on the image, and then I sum them all together. What I can essentially do is I can reweight the log probabilities for a given word, and I reweight those log probabilities based on the inverse log word frequency of that word in the corpus, in the review corpus. So in other words, if the LSTM encounters a word that is very frequent in the corpus, it will assign essentially a log probability that is highly probable, but what I do is I downweight that log probability when I aggregate things together. So what I wanted to do is really downweight the words that are very generic and kind of background or filler words. And once we do that, we get a lot better results. I would argue that all of the top four kind of sentences here are extremely relevant, and so this is also consistent across a number of different input images and a number of different listings. All right, so I'll actually talk a little bit about this because it's actually an interesting idea and it kind of is a stepping stone, as I mentioned, to the listing representations idea. So what I did before, and the model that I showed you, was essentially a conditional likelihood maximization model. In other words, a discriminative model. So we model, basically, we maximize the likelihood or the probability of text given image. Can we actually instead look at it slightly differently in terms of a generative model setting? Can we maximize the joint distribution? Can we maximize the probability of images and text jointly? And if we actually do it in this generative model setting, we have a number of different advantages. First of all, it allows us to kind of introduce a latent variable, and I'm going to talk exactly about this plate notation on the right in case people aren't familiar with this diagram. So it allows us to introduce a latent variable, and that latent variable is essentially, it represents the set of latent factors that are intrinsic about a listing. So for example, it could represent the extent to which a listing is family friendly, the extent to which it's romantic or business friendly, the extent to which it's a beach house and so forth. So we don't necessarily have kind of well-defined interpretations of each of the variables, but the idea is that, you know, in the listing space, if we did some k-nearest neighbors, these kinds of patterns would be revealed. So there's certain advantages. One is we can reverse modalities. If I had a joint distribution of image and text, I can not only condition on image and see what the likelihood of the text is, I can do the reverse. I can condition on text and see what the likelihood of an image is. And as I mentioned, because of that latent variable, we can infer representations or embeddings that use multiple modalities. So previously, we all spoke about representations of subcomponents of a listing that are unimodal. Here, I'm actually talking about learning the representation of the entire listing, but based on multiple modalities. So based in this case on reviews and images. And the way we're actually going to do that is using this following latent variable model here. So allow me to kind of describe this a bit. So we have L listings in our corpus, say, or we have, like, say, a bunch of listings. And now for every listing, what I'm going to do is I'm going to sample this variable theta from the prior alpha. And this variable theta, as I mentioned, is essentially a distribution over my latent factors. It represents, as I said before, you know, how family-friendly a listing may be, how romantic, etc., all of these kinds of things. So I have this distribution that kind of represents the intrinsic or the latent attributes of a listing. Now what I'm going to do is for each of the images I that are associated with the listing, I'm going to sample a latent variable from this latent distribution, and then I'm going to condition on that latent variable to generate the image. Similarly, I can do the same thing for each of the reviews. So for example, you can imagine that there's certain latent attributes that can only be revealed by images. For example, if it has beautiful sunset views. There's certain kind of latent attributes that can only be revealed by text. For example, if the host is very friendly and responsive. So what, you know, ideally the idea here is that when we sample from this latent distribution, we would capture some of these aspects and we would capture some of these modality-specific aspects, and then we generate the review. And this kind of chain over here essentially represents sentiment. So we can sample from a beta prior some kind of a Bernoulli sentiment random variable, and then for every review we can sample from that random variable to dictate what the sentiment of the review is, for example. So these latent variable models, probabilistic graphical models, are extremely flexible. We are actively exploring variational autoencoders, which is for me, a very exciting framework that's come up in the last few years. To do a lot of the inference and the learning here. So just to make it clear, the inference problem is essentially computing the posterior over the latent variable, so z and theta, so I forgot to add theta, conditional on the observed variables, the images and the reviews. So once we do the inference problem, we now have a representation of this listing that we can use in all sorts of applications downstream. And as I mentioned, the nice thing about VAEs is that they're kind of like a black box inference method. The thing is, if we define this model, we can essentially learn these parameters using a variant of backpropagation called stochastic backpropagation. This allows essentially us to use backpropagation, GPUs, and all this stuff to learn these latent variable models, whereas a few years ago, we would have to resort to very expensive Markov chain Monte Carlo procedures or very kind of complicated variational inference procedures that we'd have to derive by hand, and we don't need to do that anymore. So this is all very active research. In fact, the real novelty here is that whereas people have previously worked on multimodal variational autoencoders where there's a 1:1 equivalence between image and review, like for example in the caption case, I have an image and I have a caption that is directly aligned with that image. Here we have a unique problem. We have a group of images on a listing page, and we have a group of reviews also on a listing page, and we need to infer also the latent alignments between the reviews and the images in order to make this learning pretty effective. So it's a bit of a risky project, and there are a lot of areas it can fail, but if we get it right, it's also very exciting. All right, so I'm going to quickly wrap up with this concept that I've been constantly referring to throughout the talk. All of the stuff that I spoke about really builds towards the idea of learning a listing embedding. And the idea is how exactly can we represent these listings in some kind of an extensible way so that we can plug them into a variety of models downstream, all sorts of different models that we use at Airbnb. As I mentioned, we have images, we have descriptions, we have structured attributes, we have reviews. So how exactly do we utilize all of this disparate information? Well, during the talk, I presented different listing components, and I presented different ways for learning the embeddings for them. I first talked about descriptions, and what we can use is we can essentially learn a summarizer, a description to title model in a sequence-to-sequence learning manner, and we can extract the encoder embedding and use those. For reviews, there are a couple of different ideas we spoke about. One of the ones is to essentially use that P vector, that distribution or that mixture over aspects as a way to represent the information in a review. And then for reviews and images, I just briefly alluded to this multimodal latent variable model where essentially learning the representation of the listing is basically computing the posterior on the latent variables conditioned on the observed variables, in other words, the images and the reviews. So now we have each of these kind of different techniques. Are there general ways to kind of combine all of these representations into one unifying form? So the first idea I spoke about refers back to that multimodal latent variable models idea. I mentioned that, what we are currently working on is just the two top modalities. We're working on images and reviews, but we can essentially learn the set of latent factors from these two. We can essentially tack on more modalities. So in this case, it might be the amenities and the different kind of structured attributes that are associated with the listing. So we can essentially tack these on, but the problem is that it becomes a little bit of a harder learning problem the more modalities we tack on. So we're wondering how effective will this approach be? So it's still an active work of progress. The other idea we could use is something along the lines of canonical correlations analysis. To kind of give you a very high-level summary, canonical correlations analysis is exactly or very similar to PCA, principal components analysis, except what we do is we work with pairs of vectors at a time. And what we're going to learn is we're going to learn a shared latent dimensional or lower latent dimensional space, a latent space that's often lower dimensional, that essentially where the two sets of vectors are maximally correlated in that space. So you can think about, like, for example, for a listing, I might have an image vector that represents the image embeddings, and I might have a review vector that represents the reviews, and then I'm going to learn a projection of each of these vectors into a shared low-dimensional space where those vectors are maximally correlated. And then there are generalizations of this idea to nonlinear variants, for example, deep CCA. There are generalizations of this idea to more than two sets or more than a pair of vectors for this multi-set CCA. So this is another kind of approach that we're thinking about. And then the last idea that I think is pretty interesting is this concept of a combination layer. So the basic idea is, as I mentioned above, we have a bunch of these individual vectors that represent the individual modalities. The first thing we can do is concatenate them together. And then what we can do is we can then concatenate them together and then learn a projection of that concatenation into a lower dimensional space. And that ideally that projection or that lower dimensional vector representation of the aggregated vectors should also reweight the input kind of modalities in the right way. So for example, if we find that for whatever task we're interested in downstream, that images are irrelevant to telling me whether two listings are similar, then it would downweight the image component of this kind of in this combination layer. And so the idea is we can potentially use human labels and the pairwise ranking loss, which essentially makes this a classification problem, to learn this. So for example, if we have three listings, A, B, and C, and a human deems that A and B are more similar than A and C are, then we would give a +1 signal if, for example, in our k-nearest neighbor retrieval, we rank B above C, and we would give a -1 otherwise, and we could learn the parameters in this way. This obviously requires a lot of human labels and intervention. I think it also would require a large sample complexity. So one thing we could also do is look organically at booking history on the site. So for example, we could have a guest G, and you can think about representing a guest G as what I call a bag of listings. So you can take the vectors of the listings A, B, and C, and note that these are outputs of the combination layer. You can take them and sum them up, and so you get a bag of words representation of the listings. You can then take a new listing, listing D, and then we can look back at our records and see, did this user book this listing? If they did, it's a +1 signal. If the user potentially viewed this listing but did not book it, it's a -1. So you need to be very careful about the negative samples here and what you choose for the negative samples. Otherwise, the learning could take a very long time and could basically may not really result in anything meaningful. And so what we can do over here is really use the booking history to train this combination layer. In other words, to train the optimal way to combine these multiple modalities. All right, so I'm going to wrap up now. So essentially, I gave you kind of an overview, a number of different projects that the AI lab at Airbnb has been working on. And as I mentioned, the goal for us is to kind of push the boundaries of applied ML by kind of looking at what's possible, showing what's possible, basically looking at the research and looking at the literature, trying out different ideas, talking to product teams and seeing what their problems are and trying to bring in some interesting research that we can use to improve the product. I talked about listing descriptions, I talked about titles, reviews, and images. At the moment, we're kind of looking at unimodal and bimodal kind of based embeddings, but we're in the process of moving towards multimodal embeddings for representing listing description or listings. And of course, with listings, we can do all sorts of things. You know, we can come up with similar listings. We can cluster interesting listings together, recommend new listings for you, add a better element of discovery and the like. And so this is very foundational work. There's so many different ways that a good listing representation can be used for. And I just wanted to kind of give you, kind of just some thoughts in terms of how we're using neural networks to really effectively learn these representations. So thank you very much. I'll take any questions if you have.